Recording in progress.
I'll just have to come over and click.
Okay, sure. Take your time.
It's okay. Okay.
Good.
Yeah, that's what it is.
Okay, hello everyone. Welcome to the New Technologies in Mathematics seminar. And today we're very happy to have Michael Albergo from Harvard, who will be telling us about learning dynamical transport without data. Take it away.
Hey, thanks everybody. You all can hear me fine. It's not that. Would you mind sitting closer up? I kind of like, or do you want to sit in the back room? I always feel weird being in a room where there's like, you know, this way we could talk. Okay, anyway, yeah, my talk is called Learning Dynamical Transport Without Data. And the reason it's called this is because I want to stress this is not just a machine learning problem where you try to learn from a bunch of data that you have in the universe. And we're going to say that this is a problem that is approached with a non-equilibrium transport sampling setup, okay? And we're going to look at a few faces of that problem, and I want to introduce to you what the problem is that we want to solve. So the goal here is to come up with a way of sampling from a distribution given only access to the unnormalized density. Okay, so the agenda we're going to go through is to talk about annealed importance sampling and its relation to this concept in statistical physics called the Jarzynski equality. And then I'm going to state sort of more broadly the problem that we want to solve in the context of these approaches and say that there might be a way to improve on standard methods by thinking about dynamical measure transport, building maps between distributions, and using tools that people have developed in machine learning to sort of improve how we sample. Okay, so when we combine the two, we're going to get some new learning algorithms that will be able to help us sample from distributions. And then I'll, if I have time, briefly talk about a generalization of this to discrete distributions and how the mathematics has to adapt. Sound good? Okay, so this is broadly joint work with Eric Vanden-Eijnden, and then the generalizations I'll briefly talk about are with Peter Holderrieth, who's a great PhD student at MIT, and his advisor, Tommi Jaakkola. So all of the things I'll talk about today are in the context of trying to solve sampling problems with and without data that I am lucky to learn from these great collaborators, okay, but we'll mostly focus on the bottom half today for this stuff. Okay, so there's sort of two probabilistic problems that people think about these days when they think about generative modeling, sampling from distributions. Okay, and I want to state what the overarching goal is and then clarify what the difference between these approaches are by saying what you have access to. Okay, so our goal is to estimate some unknown probability density function, rho 1. Okay, the 1 will be apparent in a little bit, but just think about rho. And we want to either do this through a bunch of sample data that's given to us maybe as data in the natural world, or we want to do this through query access to some unnormalized log likelihood function, a Hamiltonian, an action in the field theory, etc. Okay, and the first one is really the paradigm of generative modeling, which is sort of taking over our lives these days. And the second is really more of what's known in the literature as a sampling problem, right? More applications in computing expectation values of functions from under certain distributions that you care about in statistical physics, things like this. Okay, also applications in Bayesian sampling, stuff like this. And what we're going to do is we're going to say we're going to try to solve these problems, right, with neural networks. Okay, that's going to be the background. And I want to give some motivation for how this sort of approach of generative modeling has evolved over the past 15 years. So just back in 2012, you know, we had the technology and algorithms to be able to sample endless digits, right? Sort of lower dimensional, but still, you know, from a theoretical perspective, reasonably high dimensional complex samples from a distribution. And then over time, these methods have been refined in various ways, such that now, just 15 years later, you can, you know, generate 1 minute long videos that are exactly aligned with a text description that you asked for within a few seconds, right? And this is pretty crazy here. I just used one. This is so out of date now, of two bears in a cartoon form doing chemistry, okay? And I want to sort of stress what has been part of the sort of you know, conceptual developments that have been behind this growth, in addition to a lot more computer power. has been, the inclusion of what I'll refer to as a measure transport perspective to the algorithms underlying these tools, okay? So what I mean by this is sort of building maps between distributions, okay? And we're going to think about that going forward. That is to say that there's it's worthwhile to dwell upon this type of mathematics to be able to think about making improvements to these algorithms and to develop new applications. Okay, so we're going to ask about, given that dynamical transport, building maps between distributions in a time dynamical way, has had so much success in generative modeling, can we apply that to the sampling problem where we don't have data, but we have descriptions of the distribution that we want to sample under, right? Analytic descriptions. Okay, so this problem, as I hinted at, is kind of ubiquitous, right? The sampling problem is really to say if I have some energy function, which is giving me, description of some unnormalized distribution, I'd like to be able to, draw samples from that distribution to study the, whatever system it is supposed to model, right? This may be a purely Bayesian inference problem where I'd like to estimate some posterior distribution as applications across the sciences. Here's an example in gravitational wave astronomy related to the problem molecular dynamics simulations, simulating the Gibbs distribution of some molecular system. Applications in quantum field theory, lattice quantum field theory, condensed matter, et cetera. This is the way we approach these problems computationally. And the tools that we use to approach them, this is probably very familiar to you all, but just to dwell on it for a sec, it's really split into two concepts, right? We have Markov chain Monte Carlo algorithms, which say, let me build a randomized sequence of samples in this state space that evolve in such a way such that the Markov chain that is constructed of them has the quality that the empirical expectation you take of any test function h as the Markov chain goes to infinite length is going to converge to the true expectation under that distribution for that test function, okay? And the very common tool people might use to do this is what we call Langevin dynamics, to basically say, initialize a sample x0, and we're going to evolve that sample in an iterative procedure by taking incremental steps according to the gradient of the potential that we want to sample under, along with the addition of some incremental Brownian motion. Okay, so if you roll out this stochastic differential equation, you'll get a walker that does something like this as it explores the state space of this distribution. Okay, the alternative is to say I'm going to import and sample. And that is to say, if I can't sample the distribution I really want to efficiently, but I do have a surrogate model under which I can draw samples very efficiently, or I have them already, then I can always compute these expectations by reweighting the test function that I need to according to these two distributions. And this is obviously only going to be effective when row 1, which is the actual distribution I want to sample under, and row 1 hat actually have some sort of overlap. So if we think about this pictorially here, I have this two-mode Gaussian I'd like to compute expectations under, and I'm drawing samples from the simple Gaussian here. Okay. So what goes wrong with these tricks? Well, one is if you have some sort of non-log concave target that you want to sample, and the modes of this distribution are spread apart, well, then the convergence of this MCMC walker is going to be exponentially slow because there's an effective non-ergodicity in moving around the state space to try to find all the modes. Here, this guy can't get to the other two modes. And likewise, if you want an important sample, but your distributions are not overlapping or have the sort of proximity to each other that you need, then the variance on the estimator you're going to get from your importance sampling technique is going to be huge, and this is going to be an even bigger problem at high dimensions. Okay, so one approach people take, really focusing on the first case, is to introduce some sort of annealed dynamics, which says initially I'm going to try to, at some time t equals 0, sample a distribution which I know to be maybe unimodal or easy to sample in some explicit sense. And then what I would like to do is anneal that distribution in some time-dependent way to end up at the target distribution that I care about. So one trivial example would be to say, let me anneal the potential just in a linear way. I have a 1 minus t u0. U0 is the energy of some very simple density, and plus TU1, U1 is my target. This is going to just define for me a time-dependent PDF. Okay, rho t, is going to be equal to e to the minus ut plus the normalization constant. I've stuck into the exponent just for moving things around. It's easier to write it this way. Okay. And what you do in this case is you'd say, let me initialize my walkers from the simple distribution. And then let me evolve them according to an annealed Langevin dynamical SDE, which says basically at every time from t equals 0, sampling rho 0 initially, increment the walkers according to the gradient of the time-dependent potential, which will continue to move, plus some Brownian motion. Okay? So what's going on here? Epsilon setting the speed of these walkers per time step, right? And you may want to structure this in generalize from some high temperature to low temperature type sampling procedure. High temperature, you're going to have unimodal type problem or something that's easier to navigate, and then you can lower the temperature. So this is what we have pictorially going on here. The blue plot is the moving time-dependent PDF, and the little red dots are the walkers sort of that initially start in this unimodal Gaussian keeping up with them. Okay. Okay, but an important question is, does the solution x tilde to this PDF to this SDE have rho t, the actual rho t that we care about as its law? Okay, what is the law of x tilde? Okay, well, it's a dumb question for me to ask because I'm going to tell you immediately that no, this is not actually always going to be the case, that x tilde actually is a sample from rho t. And why is that? Well, it's only the case if the diffusion coefficient was infinitely large and the time step was infinitely small, i.e. the walkers always have enough volatility and time to keep up with the new target potential. Every Langevin algorithm needs to mix. If I'm changing the potential too quickly, the walkers are going to fall behind. Okay, and how can we see that from, just from the math? Well, what we can do is we can compare the Fokker-Planck equation associated to this SDE with the actual time dynamics of the potential that we wrote down. We defined a rho t, we can take its time derivative, we can compare. So if we just read off the SDE that we wrote down, the Fokker-Planck equation associated to it, well, I have a drift term. It means I'm going to have the drift term here. And I have a Brownian motion, which means I'm going to have this Laplacian term here for the rho t. Okay. So this is the Fokker-Planck equation we have. And then we could just proceed with a direct calculation, taking the time derivative of the probability density will be defined. I'm going to get is equal to minus dtut minus dtft rho t. And then what I'm going to do is add on 0. And why is this term 0? Well, this is the gradient of rho t is just going to be equal to minus grad u rho t. So this term is just adding on 0. Okay. What this tells me, though, is that the Fokker-Planck equation of this guy differs from the actual time dynamics of rho t by this factor dtut minus dtf. Okay, so how the potential is evolving and how its normalization constant is going to evolve. So this means in practice, these walkers x tilde are not actually going to be in tandem with the actual time evolution density specified. So what does this look like in practice? Say I want to sample this 40-mode Gaussian mixture in 2 dimensions. Okay, I'm going to do that by starting from a simple Gaussian and then expanding the potential in the time dynamical way we specified. Okay, what you'll see, right, epsilon is equal to 4 here, the diffusion coefficient. As my potential evolves, the walkers cannot nearly keep up, right? And if I really crank up the diffusion, okay, it does a little bit better, but they're still not sufficiently in pace with the time-dependent potential. And this is to the extent that any reweighting you would like to do at this point would also be basically useless because you haven't covered all the modes of the distribution. Okay, so what is a solution to this problem? If it was a little bit better posed, because I said the reweighting wouldn't even really help you in that example. But imagine you could introduce some weights that would remove the lag between the walkers and the time-dependent density. Okay, so what we want to do here is we're going to introduce some weights that are time-dependent. There's a scalar value at, okay, such that if I look at the coupled SDE and ODE of the original walker that I have, now coupled to the set of weights which sort of compound the time dependence of the potential over time evaluated on the walker, then I can say for all test functions h of x that the expected value of h of x under rho t is going to be given by expectation over the law xt and at as I walk out the walkers of e to the at h of x divided by the reweighting factor. Okay, so this is a way of just specifying reweighting in a time dependent way. Okay, in particular, this relation appeared about 25 years ago now, getting older, from a guy named Chris Jarzynski when he was thinking about this in the context of molecular simulations that are non-equilibrium, that are driven by some sort of force. How can I sort of relate the distribution to what the walkers are doing here? And he wrote down this nice relation that basically says the expected value of these weights is going to actually give you the ratio of the partition function from where you started to where you're going. And actually, in the physical world, this is really the change in free energy is described by the average work that's being done on the system. Okay. And the way you would prove this is by actually just looking at the joint PDF of these guys, the Fokker-Planck equation of the joint PDF of these guys, and manipulating some terms around, and you'll see that you can write down this relation. Okay. What's the issue here? Well, I sort of hinted at it already. If the variance of e to the at is large, then your reweighting factor is still bad, right? So this may give you a formally unbiasing way of handling the problem, but the variance might be so bad that it's not practical. Okay, so what we want to ask is, can we fix this problem with measure transport? Can we augment these dynamics in a way that alleviates this issue of the variance of the weights? Does that make sense? Any questions?
But this is the balance of.
Let me go back a slide so you can
So
see.
this A is already solving some problem.
Yeah, the A gives you a way to formally remove the bias from your sampler, but it's going to introduce, using it is going to introduce variance into the estimators that you want. So I'm trying to compute the expectation of h of x, right, under rho t. And then I have a definition of that expectation over whatever process I have here and the weights. But the variance of this guy might be really bad if the variance of the weights is bad. So what I would really want is that I could get, put another way, if the variance of this term is really big, then it's going to take a lot of walkers to get an estimate of what the ratio of the partition function is. But if the variance were 0, then with a single walker, I could extract what the partition function is. And I'll try to motivate how we actually can retrieve that 0 variance limit of the weights. Sound good? Okay, quick detour into measure transport. Okay, so in this case, just introduce a little bit more notation, because that's fun. We're going to think about the problem of maps between distributions, and to do that, we're going to think about a flow map, okay, which I call here capital X t, which basically says that at every time t, given a sample, for example, a sample x0 from row 0, the flow map x, capital X, is going to assign that sample from some time to a sample at another time, right, along this trajectory of the distribution. So I can imagine a continuous deformation of my row 0 into a target row 1, and then at every point there are these characteristic curves mapped out by the flow map that says x is going to be mapped at time 0 to another x at time t. That's xt of x. That make sense? And the way you define this flow map is through the solution of an ODE, where a vector field bt takes in xt and tells you, what's the velocity of this particle, if we think about it this way, along these characteristic curves. Okay, so that's happening at the level of the samples. And then you can ask what's happening at the level of the distribution, right? I'm saying these are the trajectories taken by any individual samples such that they can be assigned to another sample underneath the distribution forward in time. Well, the density itself must satisfy some sort of transport equation, which basically is a conservation of probability density equation, which is basically saying that the time dynamics of rho t are going to evolve according to the divergence of this product of this velocity field and the density itself. And we would say that the pair bt and rho t solve this equation if starting at rho t equals 0 is equal to rho 0, I end up at my target rho 1 later on. Okay, so I need to find the bt that would do the job for me here. Alternatively, I could add 0 to the right-hand side of this equation, like we mentioned before, which would be to say, put on, grad rho t is equal to minus grad ut rho t, stick this on the other side, and now I have a Fokker-Planck equation, which is going to say I have some sort of stochastic mapping, okay, from some initial condition to some other sample in the distribution. Okay, so this is sort of the deterministic flow, and this would be the stochastic sort of diffusion that we think about. And importantly, if I have the BT that does this, then I can stick it into the Langevin SDE we were writing down before, because this part and this part are just sampling the equilibrium distribution at any time. And this guy is going to drive the map from rho 0 to rho 1. Well, then I can say, if xt solves this SDE, or I've dropped in this new drift coefficient b, then xt is a sample from rho t for all time. Okay. So what if I don't have the perfect b, and I want to use this b in the equations I've had before to lower the variance of the estimator for the expectations that I was trying to compute? Well, let's imagine that we take this b that we've given ourselves. It may not be the right b that actually solves the transport problem, but it's some b. And we take the left-hand side of the continuity equation where I have this divergence term, and I expand it. And I just add this term to the left-hand side of the equation I had before, and this term to the right-hand side. Okay? Now what I have is an equation that says this term 0 by design. Here is my new non-equilibrium term, this term that separates the dynamics of rho t, right, from the Langevin dynamics that we had initially. And what I can do is, before what we did, just to go back, refresh the mind, we said there's this non-equilibrium term which separates the dynamics of Fokker-Planck equation associated with the SE I have and the dynamics of the rho t that I actually specified. And we said, if I look at this term, it's accounted for by the weights here. Now I would like to say, I have a new non-equilibrium term. So damn it, it should be the weights here if I want to use this BT in my sampling algorithm. Okay, so what we can say is that if we add in an additional drift, there is still a principle under which we can compute importance weights a la Jarzynski, so that we can take expectations of any test function. Okay, and now the question is, how do you find the BT that actually makes the variance of this guy small? So we've introduced a mechanism that changes the transport, and now I want to find the best mechanism that we can come up with. Okay. So this relation, I should say, is about 20 years old. It hasn't appeared like this, but there's also some work by Francisco Vargas and folks who derived this in a different way using Girsonov's theorem. And here we just sort of do it by manipulations of the PDEs that we have to work with. Okay. Right. So this is what we would think about as correctable dynamical transport. If I can change my B, I can sort of adapt my sampler to find the best sort of estimator I can, keep this variance low. And it's in some sense just a strict augmentation of annealed Langevin dynamics. We had the Langevin dynamics, we've stuck in an option here that's a knob now for us to change the variance of the Langevin dynamics.
What, and maybe what's the interpretation? Is there an interpretation, or how can I think about this? Like the other technical?
An interpretation. So
maybe
the way I would interpret it is to say Langevin dynamics is like an equilibrium sampler. If I run it on a fixed density, I'm going to ultimately sample that density. Now we've made this Langevin dynamics annealed, so it's always out of equilibrium. And we say, okay, if we just kept running it for long enough, it would equilibrate on the distribution that we have, and then we could change the time for that distribution and march forward to the next target distribution in our sequence of distributions, right? And now we're basically saying, you can continue to do that, but you could also just solve the transport problem exactly with the flow. And if you solve the transport problem exactly with the flow, it doesn't affect the fact that you can still run Langevin dynamics at any time. But it would mean that you would always remove the lag from these walkers if you use them in like a, a quick way to map from rho 0 to rho 1. And that is to say, if I remove the Langevin dynamics and I just kept B, and it was the B that solved the continuity equation, then this would also be sufficient to sample from the distribution. In that sense, you mean it's valid for any diffusion coefficient. Be 0, could be infinity.
So do you have a B and B hat, or is the hat as well? Can you just remind me what's?
Oh, sorry, this should have a hat.
Okay.
That's just a typo. Good catch. Yeah. Okay, so now we want to figure out how do we discover the B that does this, right? We have this now very long equation, which basically says, I had a moving time-dependent potential that gave me this non-equilibrium term in my dynamics for rho t. Now I'm stuck in a anomalous C dot B hat. And so I get this term too over here. And what I either need to do, what I was just saying, is if I've solved the transport problem, right? This is equal to 0, the continuity equation is solved. Okay, that's one solution to figuring out what B is. And the other is to say I'd like to remove the non-equilibrium lag, right? I want this whole part of the equation to be 0, because if it is, then I'm back to the solution to the transport that I said before, which was just the pocket block equation, right? Those are the two knobs you have. And so if we think about the second one over there, you can write down what's known in maybe the literature as a physics-informed neural network loss, which basically says, let me just solve this PDE, if I set it equal to 0 everywhere in space and time, and take this, square it, it's some residual that you want to go to 0, and you minimize this over all B in your parametric class and all parametric representations of the free energy, so some neural network that takes in time and outputs a scalar. And if you do this, then the solutions are such that this guy is equal to 0, ft that you get out from this parametric search is the free energy, and BT solves the transport problem, okay? And so what's nice about this loss function is it's valid for any rho hat, rho t that you take. Just, you want to solve this thing really everywhere in space and time, but where you really care about solving it is over the trajectories that your walkers would take. But this means that you don't need to use samples from the true distribution to actually evaluate this loss function. In that sense, it's just like off policy in some sense to connect to the ML literature. And that means you can store a bunch of samples that maybe you've generated and continue to minimize this loss function over samples that you already have, keeps it a bit more efficient. Okay. And notably, if you minimize this, or if you've got this under some value, well, this thing is going to control the KL divergence between your model rho hat and the true distribution rho. Okay. The alternative is to set up a loss, what's known in the literature as action matching, which basically says if I learn B in gradient form, so I parameterize some scalar function, I take the gradient of that scalar function, then I can minimize this objective, okay, which you can just see that the Euler-Lagrange equations associated with this guy be this, some manipulation, and this is another valid loss function. But it needs true samples from the distributions, so you'd have to use your weights in the evaluation of the loss. Okay, so what happens if you learn B? Before we had a Langevin dynamics with epsilon t equals 4. These guys were not keeping up with the time-dependent potential at all. If you learn the B, as we did with the pin loss in this example, now we have this extra drift, which is ensuring that every sample is escorted to where it needs to go along the time-dependent potential. Okay, so this, if you were to run, annealed importance sampling, this annealed Langevin dynamics alone, without the transport added, without the B, okay, this is where you'd end up. You'd have an effective sample size of 0.7, but really 0. If you just learn the transport and keep the diffusion coefficient off, so no of the local mixing, then you can get an ESS of around 95%. And then if you turn the transport, the diffusion back on, because this was valid for any diffusion coefficient, then this ESS is going to continue to climb up. And why is that? Well, we said in the beginning that if I could run the annealed Langevin dynamics infinitely slowly with an infinitely large diffusion coefficient, well, then it would sample exactly. And this means at our limit, we still benefit from that fact, okay? So the more diffusion I use, the more accurate my sampler will be, given that you can actually integrate those equations under your computational budget. But learning the transport is like a preconditioner on that, right? It's telling you, you learn this drift as well as you can. That's going to help use whatever diffusion you want on top of that. Okay, so let's look at an example of this. Generally, there's been a lot of interest in augmenting MCMC algorithms with transport. Okay, but they have this issue that in high dimensions, the benefit of the learned thing sort of falls off exponentially with the acceptance rate of your Markov chain, things like this. The metropolis ratios get bad. And so what we want to sort of argue is that now that you have this diffusion knob to play in with these measure transport type problems, you have this tool that sort of allows you to still reach this perfect performance limit. So what we want to do here is sample a Gaussian mixture in high dimensions. Here are cross sections of it. Just grab 2 dimensions and look at cross sections. And what I want to do is look at this Gaussian versions of this Gaussian mixture in higher and higher and higher D. So going from 36 dimensional to sweeping up to about 200 dimensional. And then I want to ask, what happens if I take that pin loss and try to find the vector field B that would solve the transport for me, using the same neural network for each of these higher and higher dimensional problems? Okay, so we're not increasing the parameters run to run. We would expect there to be a fall off in the performance as the dimensionality gets bigger because the problem is getting harder and we haven't given ourselves any more tools. So if I look at the x equals 0 part of this plot, what I'm looking at is the diffusion coefficient that I choose to use to do the sampling and the effective sample size that I get at that diffusion coefficient for the various higher and higher dimensional problems. So each line is a different dimension. What you can see as the dimension of the problem goes up, my ESS starts to drop at this point because I'm not using any of the diffusion. I'm just relying on the transport that I've learned. But as I turn the diffusion coefficient up and up and up, you're going to return back to this 100% effective sample size limit as the diffusion gets larger and larger. And what's worth noting is if I try to take this limit without the learned transport, I don't get to really see that benefit. I never get out of the 0 here. Okay, and so what this is telling us is that diffusion helps more if you've already learned a little bit than if you haven't learned at all. Okay, so it's actually more of a realizable limit, this infinite diffusion coefficient limit of perfect sampling, if you have some transport, even if it's not good enough. Okay, so then we apply this, another example to sampling of 5-4 model, which is like a continuous relaxation of the Ising model. So what do we have? We have a system that can be magnetized. All of the lattice sites can be positive or negative. Sometimes they all become negative. Sometimes they all become positive, depending on the parameters of the time-dependent potential that you write down. Okay, and what we want to do is see if we can approach the critical point of this phase diagram. You choose the parameters of this potential such that there's this sort of maximal correlation across the lattice. And over this critical point, you'll get these magnetized samples where everything is all positive, where everything's all negative. Okay, and so if you just do this with AIS, the annealed importance sampling, you can get an ESS of around 1%, maybe a little less, 0.5%. And if we do this with the transport, we can keep this about 2 orders of magnitude higher than the other case. We can just sort of sanity check that the distribution of the magnetization of these lattices matches what we would expect. And indeed, you can do this over the phase transition, which kind of surprises us, into this double weld magnetized phase. You see, the absolute magnetization is going to be positive and negative at this point. Average magnetization. Okay, so why is this not totally a little free lunch? Well, one, you have to learn a neural network and then add it to your sampler, and that's obviously expensive. And the other is you need to be clever about how you actually choose the potential that you're going to take, right? So I just sort of wrote one down at the beginning of this discussion, which is like linear interpolation of some u0, 1 minus tu0 plus tu1. In many cases, that's actually a horrible choice. And to motivate that, if I had some Gaussian at -5, and that was my u0, and I wanted to use that to ultimately push samples to be under some Gaussian at +5. Well, the interpolation with that UT would actually result in this weird teleportation of mass. I would need samples over here at time 0 to just appear basically over here as the distributions are sort of reweighted. That's what that interpolation would result in. And if I asked a velocity field to push samples like this, well, that would mean instantaneously it needs to go, a magnitude of 10 or something like this. And that's totally, unreasonable when it comes to thinking about like integrating an ODE or something like this, right? What we would really like is that there's a geometric interpretation of the transport such that you actually, move the distribution over to the target, right? So this kind of looks like a version of optimal transport, but we're not going to assume that that's what we want to aim for, because finding OT in general can be hard. And so what we're going to think about this for 1 sec is imagining the path that a diffusion model might take in generative modeling. Okay, when you've seen these examples of you take a Gaussian random image and then you slowly diffuse it into an image of a flower or something like the bears that I showed earlier. Well, that path actually has some nice properties. And the question then is, how do we realize it? And we'll think about that briefly now about in this perspective that we call stochastic interpolants. Okay, so we're trying to come up with a way of getting a good path between our distributions, because that's going to be more favorable for the types of transport that we want to learn. And so what we want to do is quickly introduce this interpolant function, okay? This interpolant function is a function of time, samples from the base distribution and samples from the target distribution, x0 and x1. And has the property that at time t equals 0, the interpolant will evaluate to x0, and at time t equal 1, it'll evaluate to x1, okay? So what's a simple choice? Well, we could just do like 1 minus tx0 plus tx1, which looks like the linear interpolation we were doing before, but now it's at the level of the samples rather than at the level of the distribution. And in particular, if we draw x0 and x1 from some coupling, could be independently drawing them, they could be related somehow, then what we would say is IT, this interpolant function, is actually a stochastic process which samples some rho t, some time-dependent distribution. And for example, this is what we would get if we did the linear interpolant. Okay, so there's a smoothness to this. Okay. And then, of course, associated to this, there's a BT with this rho t such that there's a flow map which would map samples x0 under rho 0 to samples x1 under rho 1. And in particular, the BT that does this has a form that's related to the interpolant that you choose. It's going to be given by the conditional expectation of the time derivative of this interpolant conditioned on that the interpolant is equal to x. So that's the velocity field at x. It's basically telling you if I tried to pair all the samples x0 and x1 by randomly drawing them, then the velocity field is the average of all those lines I would draw in the direction, with this magnitude. Okay. And relatedly, you can write down what the score of this distribution would be too in terms of the first coefficient, alpha t in the interpolant. Okay, so what this means is it specifies a BT without ever having to write down what rho t is. I didn't say what it was, I just gave you a BT and then I said this is the path that you would get for the samples. And our challenge is going to be, can we actually learn the UT associated to this interpolant? What is the potential associated to this interpolant that I wrote down at the level of the samples? How am I actually moving through probability space here, huh? Okay, so quickly, there's just a little relation that says the velocity field can actually be defined in terms of the score functions, okay? Weighted by these coefficients alpha and beta that define our interpolant. And if I choose like a simple alpha and beta, like the square root 1 minus t squared and beta is equal to t, then this relation is really explicit. Just says the velocity field is going to be equal to x over t plus the score over t. And so what I might ask is, instead of trying to learn the velocity field B explicitly, given that this relationship exists, what if I parameterized the time-dependent potential for the non-equilibrium sampling algorithm that we use that says, start at the Gaussian, this is my 1 minus t term from before, go to my target, t times u1, and then put on in the middle, disappears at the endpoints, a neural network, okay? That's going to change the potential everywhere that you want to learn, this ft hat. And if I can acknowledge, okay, that the gradient of this guy is going to be equal to minus the score, but that's what grad u is, okay? Grad log rho t is equal to minus grad u. Then I can learn B using this relationship, okay? Such that what I end up with is a parameterization of u that gives me the interpolant path. Okay, so if I have this guy, this defines a score, This defines a velocity field. Then I use the same loss as before, but my parameters are now in U. And I minimize the loss according with this relation, then I actually learn to sample along the interpolant path. And so this is what that would look like over there. And so this is going to be one avenue toward getting to this, but it's a little difficult to optimize in practice. Okay. But that's just a comment to say that there's still some challenges to figuring out how to solve this problem. Okay. And the last thing I'll say is that recently with Peter Holderrieth and Tommi, we've been thinking about extensions of this away from this continuous setting, but to discrete settings for continuous time Markov chains. Okay. So before, what we wanted to learn was this vector field B hat, right, which solves this transport equation. And in the discrete case, where I have some X or Y that's from a discrete state space, maybe it's 0 and 1, like an Ising model. Maybe it's the tokens associated to the vocabulary and language for large language models. Okay. What I want to do is find the rate matrix QT, X and Y, that tells me what is basically the rate at which a sample X will jump to a sample Y that are different states, different items in the state space. Maybe just for context, if this is a language model, something like this, X is some sentence and Y is a neighboring sentence that differs by one word. I'd like to know the rate at which this process might jump to that. Okay. Well, then what I need to do is find the QT that solves the Kolmogorov forward equation, okay, which is basically the discrete tool equivalent of our continuity equation here. And then if you do this, you can write down the sort of discrete pin loss, which looks like the pin loss we were using before, but now it just involves terms that are violations of this equation rather than violations of this equation. And to make this sort of scalable, basically, because we need to take these sums over Y, there's some new symmetry that we need to impose on the neural network architectures to get this to work. But if you do those, you can now sample from, Potts models, Ising models using this type of technique. Okay, so this we put on the archive in February. And that's all I got. Okay, so this was a dynamical formulation of unbiased sampling. Okay, that's augmented with transport. And the nice thing that is maybe practically favorable about it is that the loss functions don't require you to back propagate through your sampling process. This can be made efficient. So this is sort of a pin off policy loss. And if you want to look at one more GIF, this is how these Ising models would evolve toward their magnetized state trajectory. Okay, thanks very much.
Any questions for Michael? Also on Zoom.
Can't see this yet. Let me see.
Hi, Michael. A question from Zoom.
Someone speaking in the ether.
Hi, I'm someone from Zoom. Can I ask you a quick question?
Yeah, I can mostly hear you.
Oh, okay. Can you hear me now?
Yes.
Yes. I have a quick question about generalization. So given what you presented, I can see that it doesn't matter. You'll just evaluate the sample through pin loss or particle-based loss so that you can learn the sort of the control force B over the path.
That's right.
But I'm imagining the scenario where in the actual physical process, there's this given true function so there's a functional form. So even if you don't show the part of the path, just by showing the other half of the path, maybe you'll be able to learn the functional form of the B such that it can generalize to the path that you didn't show. So I think that 40 modes example is unfair because if you just try to get to the 20 mode and see how it does to the other 20 modes, I guess it wouldn't work.
Right.
But could you be able to somehow enforce this notion of generality for your B? And I guess I'm asking this because that off-policy aspect is quite nice because its own policy you will never be able to generalize because
that's right.
Yeah.
So that's a good question. Let me say one thing about why the generalization can work in practice, or at least my intuition for it. I wrote the pin down as an integral over the whole time interval that we want. But in practice, you can actually solve this in an annealed fashion. So if I find the b at time t equals 0, now I can use it to exactly sample the distribution I need at time t equals 0.01 or something. You know, if I take one step of Euler integration with the velocity field I've learned, and you know that once you've minimized the loss to 0, that the b now is the exact tool that you need to sample the incremental next distribution. And then you can minimize that part to 0 and continue onward. So the annealing allows us to avoid having to think about this sort of half functional form that might require some sort of symmetry or something like this. And that's kind of the appeal of the pin, is that we know when we've solved the problem and can continue on.
I see. Thank you.
Yep.
Maybe I can ask a quick question.
Yeah.
Without the B, I think that you mentioned it, the SDE is equivalent to a deterministic ODE.
I'm trying to click. This guy.
No, I think in the beginning, maybe without the B, I
These guys.
think so.
So if I removed these terms.
No, the B. If you remove the B, you can trade the SDE for an ODE. Deterministic ODE, right?
No, if you remove the b, then all you have is an SDE. And if I remove these terms,
Yes.
then I have an ODE. Right? Because all I'm left with is the b. This is the stochastic part.
Right.
So if I lose these guys, the point is that this will actually still sample the same distribution at every time. Just do it in a deterministic pairing versus a stochastic pairing.
Without the B.
No, with the b.
With-
You need the b if you want to make this leap to say that the marginals are the same. If I remove the b, then this goes back to the x tilde that we had before, which had a different.
Right.
If I remove the b, then I'm here, which says this x dx tilde has this Fokker-Planck equation, which is not the dynamics of the rho t that I specified. And if I add the b, then I've so the relation here is it's slightly different. It's basically saying, okay, it's basically saying, we know that this sampling according to this, if I fix time, is like equilibrium dynamics. If I remove this guy, this will just sample at, if I keep this at t equals tau, I fix that and I just iterate this guy. That'll sample rho tau in the equilibrium limit of things, right? But now I'm saying if I put the b in, that solves the transport problem. Then every sample from x0 is going to be assigned to a sample xt from rho t, and that's a mapping. And now I'm saying that's always happening. I can just stick on Langevin dynamics as well, which is in equilibrium dynamics. That'll say I'm going to have some sort of diffusion, but the marginal distribution rho t will be preserved at all times. So this guy is the same as this guy in law. That's the difference.
So we have a question in the chat. In practice, is the overall normalization partition function of ut guaranteed to be fixed over time?
No.
Okay.
It would be kind of nice, I guess, if you could choose one, but like if you choose a U0, like ultimately, no matter what, the path that you take, you end up with these weights giving you the ratio of the partition functions. So unless this is one by design, then by this problem setup, then no.
Okay. Any more questions for Michael? If not, let's thank Michael again.